Hello everyone. Today we'll see a control system example and solve it with using YALMIP in MATLAB. So the example for today is minimum energy and minimum fuel optimal control problem. So let us see the problem formulation. Okay. So there is a discrete system whose difference equation, discrete time interval system difference equation is defined as this: xk plus 1 is equals to axk plus buk, and ABC matrix is given. So the goal is we have the initial condition x0 and a final condition xe, and we have to find sequence of u such that total energy is minimized. So our first question will be, let's say for t is equals to 10, or if we run for 10 seconds, so what will be my sequence of inputs so that the total energy is minimized? And the problem is, what will be my sequence of u such that total fuel is minimized? So you can see the formulation. So the objective function in case of minimizing energy is summation of uk square. Okay. And the objective function in minimizing the fuel is minimizing the summation of mod of uk. This is this you can study in theory why this comes and what are these representations. I will not go in that detail. So the simple representation is this. Here we have the uh, s- here we have the initial states and here the final states, and there will be some sequence of u which will move it to the final state. Okay. So, and also we have to compare the plots on a in MATLAB. Okay. So we'll use YALMIP here to solve the optimization problem, and we'll see. Before moving forward with MATLAB, we have to first see how can we frame the objective functions and the problems. Okay. So if you write the expression, solve this difference equation and write the expression of xk, which I have written here. Okay. So if we start with, let's say, k is equal to 0 and write the equations like this. So you can see we can formulate it as a xk can be written as this equation. Okay? And this matrix b a square b a k minus 1 b is called controllability matrix, which is written here as dk. And I have a matrix of these inputs, this sequence we have to find. Okay? So this is your equation of xk, which is true for all k. Okay. So if we want our to be on to be on final position xt, which was defined in the problem here, xt 20 20 20. So at t k is equals to t, this equation should hold. Okay. So we'll put t, and this will be one of the constraints. Okay. So for minimum energy, the problem formulation will be like this: minimize u transpose t. This is basically just the sum of square of the each elements. If you do this u transpose u to a column vector, okay? Another constant comes from this equation. Xk is equals to a to the power k x0 plus ck and this u vector. So this u is basically a vector here. This is your constraint here. And for minimum fuel, we'll see the minimum fuel problem later. Let us first solve the minimum energy problem in MATLAB. Okay, so let us open the MATLAB. This video may go longer. Okay, so don't worry. So these are the matrices defined. X0 and xt is defined, and t as answered the question is defined as 10. So I'll run it. So this will initialize all these matrices. Okay. So we have to first form the controllability matrix. Okay. The ck matrix which we are defined there. So let us initialize ck is equals to a empty matrix, and for k is equals to p minus 1 to 0 with a step of minus 1. Okay. In this way, we write the for loop. This. Okay. So ck will be ck and then comma a to the power k into b. Okay, so this will accumulate all this a to the power k, b to the power minus k, b, and all this matrix elements. Okay, so I'll end it. So now we have to define a variable for the YALMIP. So I'm defining as TP word. So this will contain T elements, T initial T U values will be there. Okay, so these are the decision variables. So our objective function will be U1 transpose into U1. This is our objective function. It is simple as that. So constraint one will be Tk into U1, which is all, is equals to x at t minus a to the power t. It was a to the power k, so time t it will be a to the power t into x of 0. Okay, so the constraint is defined. So now I have to define options. So let's say option 1 as TP settings. So we have to need a solver. So I'm using just Mosaic solver. It is very, it is up to you to solve using any solver you want. So verbose I'm setting 0. I don't want to see the results, all the data of the results. Okay? And I'll see what is the error. Oh, yeah, for that we need to solve it also. No? So solution 1 will be optimize constraints 1, then objective function 1, and then OPTS 1. Okay, so this will give me the solution 1. So we can now write solution 1 dot problem. So to print like what is the status of the solution. So now our U optimal solution of U will be value of U1. Okay, so this problem will be solved and we'll get the U optimal. So we can see results if it is solved or not. Okay, okay, we are getting some error. Yeah, this is this. Okay, so this is the error. Okay, so we got our values. This is the optimal value accordingly for this minimum energy thing. Okay, so now let us see how we can formulate the minimum fuel problem. Okay, so we saw that for minimum fuel problem, absolute sum of this UK should be minimized and same, the constraint will be same. Okay, for t time. Now this absolute sum is not a standard form representation. So we'll try to represent it in a standard convex form, convex approximation form. So let's say that UK is equal to TK, this variable TK. Okay. So since it is an absolute value, so TK will be positive. So there is one constant TK is positive. Okay. And you know, if something is equal to something, these two constraints will only be true if it is equal to TK. Okay. Got it? Let's say UK is less than TK and UK is greater than TK. So UK will be equal to TK only. Okay. So this constraint you can see from the any formulation you'll see these constraint will be there. Okay. So now our formulation is like this. So let us formulate it. So minimum fuel problem. We'll start from here. So it will be in similar manner. We have earlier defined CK matrix, so we do not need to define it. So we'll just need STP var t comma 1. Now we'll also need a separate variable t STP var, which is also same as capital T. Now the objective will be sum of this t. Okay? This is the absolute value of the u. Okay, understood that problem? Now a constraint will be what. So first constraint is similar. So let us copy this. So the first constraint is similar. Okay. Now this second constraint is u2 is less than or equal to t. Okay. Third constraint is minus of u2 is less than or equal to t. And fourth constraint is t is greater than or equal to 0. Okay. So these are the four constraints which we have defined. Okay. Okay. If you want that u is between some limits, you can put that constraint also. U is suppose u is less than 100 and u is greater than minus 100. So you can put that limits also. But right now we are not putting that limit, but obviously you can put constraint. Then then it will be more conservative problem, and it may also give no solution. Okay, in that case you have to be careful that what limit you are putting. Okay, so now our options will be same as CP setting. So let me copy that only. Okay, so our options are same. Solution 2 will be all things are same, so you can directly copy it. Okay, so solution 2 is same. Okay, constraint 2, objective 2, then option. So solution 2 problem status, and then u optimal 2 value of u2. Okay, so let me come with the semicolons here also. So that now we have to generate trajectories to see to plot on the same graph. We also need some trajectories. Okay, so I'm generating some trajectories. So let's say xk1 is equals to x0, xk2 is equals to x0. That is for second case. So x1 is equals to x0. This is to store the history, just to store histories of the data. Okay. This is also x0. Okay. So for k is equals to 1 to t, xk1 is equals to a into xk1 plus b into u optimal 1 of k. Now, after giving the value to xk1, I will store x1 as x1 comma xk1. Okay. Now the xk1 will be updated. So it will be updated in loop. Okay. Similarly, it will be same for xk2 also. So I'm giving xk2, xk2 optimal of 2, xk2, x2, then x2. Okay. So the values are stored here. Okay. So now we got the values. Now I have written a code to plot the data. This is just to plot, just a plotting thing. So I have defined time from 0 to t1 and plotting the u. So we can see the graph also of the u. On the same plot, I am plotting u optimal 2 also. There is a plot for the states also. So I have plotted states of x1 and then states of x2 on the same plot. So we can now run the whole code and see what we get. Okay. Okay. If we run this section, it is successfully solved. If I run this section, it is also successfully solved. Now, if I run this section, trajectories are generated. Now, if I run this section, will get the pops. Yeah. Okay, we got some problem in states of 2. Let me check what the problem could be. Okay, so are we getting the values of optimal or not? Let us check that. Are we getting any values or not? Okay, yeah, here we are not getting any values. So what could be the reason? Okay, let us solve it here only. What could be the reason that we are not getting any values? So we had to optimize the sum of t. This is correct. Okay, yeah, here it is u2. Now, these kind of mistakes can always happen. Okay, so this minimum energy problem is solved. Minimum fuel problem is solved. Okay, now we are getting the values of u. This trajectories are generated, and now we got it. Now you can see all these states are uh, coming to the point 2020. 20 red one is going also to 20, yellow blue one is also going to 20. Okay, this is a kind of similar nature of the states. We have not put any bound on the state. Anytime if you want your states should be at particular location, you can give that as a constraint. Suppose I want time is equal to 7, my state should be at 0. Then you can put that as a constraint. If it is solvable, then it will be solving. This is your U. So the red one is minimum fuel problem. You can see it is 0 for almost 6 seconds. So it is using no fuel for 6 seconds, and then suddenly it is deaccelerating and then accelerating. That is required for the acceleration of these states. So it is minimizing the fuel. And in this case, the area under this U curve is minimized. This in this blue one case. Okay? So it is minimizing the energy. Okay. So in this way, you can solve optimal control problem, the minimum energy and the minimum fuel problem. This is just a simple example for that. If you want some constraints at different time, you can add the constraints here. Okay. So yeah, thank you. We'll meet in the other lecture with some other problem. Thank you very much.